Yeah.
Perfect timing. Okay. Since you are here, we want to run the slides. I can jump to Keccak. Do you have HTML?
Plug in. So maybe we can start saying hello.
Okay, hello everyone, and welcome to the Thing to Thing research group session here at IETF 100. We'll just plugging in cables, and we'll be starting in a minute. Projector is off.
Oh, that's nice.
What? And we will be using the Etherpad for the collaborative note taking, but I just noticed that in the agenda page, the link is broken. It has a IETF in the URL, it should IRTF. But I sent the correct link on the Thing2Thing Research Group mailing list earlier today, so you can find it in the emails, the Etherpad link. Or if you click the link on the agenda page, just change IETF to IRTF and it's fine. Dave? Okay, so now it's better. Okay, excellent. So yes, just to repeat, the link on the IETF agenda page points to wrong Etherpad. The correct Etherpad link was sent to the Thing2Thing Research Group mailing list.
Yeah. You want to start? Okay. Okay, so welcome to the Thing2Thing Research Group. I'm Carsten Bormann. This is Ari Karinen. This is an IETF meeting. So the IPR guidelines of the IETF apply. You can find more about them under IRTF.org/IPR. Blue sheets are going around. We have note takers, I believe. A few pointers here. We have a mailing list, and in particular, we have a repository that will collect all the information for the meeting today. So on the agenda, we have a quick introduction and research group status, short reports from 3 meetings we have had, and then we will go into 3 topics that will be described by 4 talks. And actually, we're probably not doing any big wrap-up in the end, so we will just do the meeting planning part up front. So to remind everyone what the Thing2Thing Research Group is, again, it's a research group, not a working group, and we look at research issues in turning through Internet of Things into reality. So Internet of Things for us means an internet where low resource nodes can communicate among themselves and with a wider internet. And within this really big subject, we look at issues that have opportunities for IETF standardization. And we do this full stack, so we are not bound to any specific IETF area. We start at the IP adaptation layer and we end at human rights. Looking at what the research group has been doing, we have a pretty packed meeting schedule, so we try to juggle and keep a few balls in the air. And one of this is the WIShy activity, where we look at semantic interoperability. There are about 10 standards development organizations that do work in the area of defining semantic tags for things that happen in the Internet of Things. So what is a door log? What is a temperature sensor? And what does the temperature that comes from it actually mean? And we're trying to bring these together, and this is the WIShy activity. And that's one of the activities where we have regular calls. And we also had a hackathon that we will be talking about, and where we will have a follow-up call because he couldn't complete the work during the hackathon. We are working with OCF as one standards development organization, and again, we are going to have regular WebEx calls with them. That's something we decided on last Friday, and we will start doing this in calendar week 49. We are working with W3C, Web of Things, but we don't have a meeting scheduled, next meeting scheduled at this point in time, so we're looking into 2018 there. We have one interesting opportunity for presenting new work in the area of IoT security. We have a workshop at NDSS. The submission deadline is December 1st, So you may want to look at the call for papers that is linked on the agenda. The subject is decentralized IoT security and IoT security standards. And in 2018, we plan to use the IETFs as opportunities to get things done. So we probably are going to use the hackathon format even more. And we are also looking at joining hackathons of other organizations. So the OCF, for instance, has a regular Plugfest, and we are looking into maybe joining them in the Malaga Plugfest in April. So this is a quick overview of what will happen meeting-wise. Document-wise, we have one research group document that has been going on for a while, which is the state of the art and challenges for the IoT security document that actually started out in the core working group, and the core working group never quite knew what to do with that. It turned out that the research group is a much better venue to get such a document completed. So this is now really getting ready to publish, and if you haven't, there's no link here, we should have put a link there. If you're interested in security, that's a document you may want to look at and maybe provide some feedback for. We also recently adopted another document, RESTful Design for IoT. And this document collects a view on how the REST paradigm can be used in the Internet of Things. And this recently got new text on hypermedia-driven applications, on system design and hypermedia controls, and more generally on design patterns. How do you do procedural calls in a REST environment, and why you really don't want to do procedure calls? How do collections work? How do you convert? How do you represent events as state? And how can you represent a concept that is often called server push? So these are two documents we're not going to discuss today, but where we thought it would be good to provide pointers to. Now I would like to quickly report from a two-day meeting we had in Berlin in conjunction with the RIOT Summit. RIOT is an operating system for the Internet of Things that has a lot of developers out there. So there are probably 1,000 people who actually work on or with RIOT. They have regular meeting, which they call the RIOT Summit, and we used the opportunity to collocate with them and also with the ICN conference. So we had some pretty good research representation. This meeting had a lot of topics. I cannot really do justice to it in a couple of minutes, but I want to provide 3 highlights. One is we had not planned that, but for some reason we broke into a discussion, what is the Internet of Things? And this is what came out of that. And maybe we can take that as a draft working definition for our own use. So the Internet of Things is obviously composed of things. And an Internet of thing is a node on the Internet that also has a foot in the physical world. So if it's just a router or a cloud service or something like that, it's not really an Internet of Things device. But the interesting part about Internet of Things device is they have a physical presence, they do something in the physical world, they sense, they actuate, and often with a narrow purpose. And why this says not just for talking to humans, just so we don't have to include smartphones or similar devices as IoT devices. Of course, there are IoT devices that are being operated by humans. So a light switch, of course, always talks to a human. That's its purpose. So we're not excluding that, but the point is the light switch is situated in a certain physical location, and that makes it an IoT device. So the physical relationship, that's one interesting property of the IoT. Another property that is often cited is constraintness. So IoT devices are often constrained, but certainly not always. So a robot, an industry robot that costs $100,000, that certainly is an IoT device, but a very different one from a light switch or a temperature sensor. And given that we expect a large number of things to come up in the next few years, scalability is an important property, and that leads to a third property of the Internet of Things, where we assume some frugality in cost, in power usage, in other resources, in human attention, and so on, which makes it a bit of a different environment than other parts of the Internet. So that was a pretty interesting discussion we had in Berlin. Another interesting discussion was about coexistence. We already had a short segment on coexistence in the Chicago research group meeting, where we had a number of ad hoc breakouts to certain topics. And the situation right now is that all of us are designing the Internet of Things as we would be designing a car that has the road all for itself. And of course, that doesn't work. At some point, you need direction indicators and other items that cars for themselves certainly don't need, but they need it in a situation where other cars are on the road too. So we are trying to understand what are the interesting properties of a more crowded landscape. Obviously, spectrum is one point that immediately comes to mind, but there are also other aspects. And how can we avoid one IoT network taking out the next IoT network by using the network or the spectrum or other shared resources in bad ways? And can we establish some collaborative usage of certain shared resources? For instance, spectrum management. The IETF already has had a working group on spectrum management in the white space, the TV white space world, and the discussion is heating up on how we are going to manage new bands that are coming up that will not just be unlicensed, unmanaged bands, but that will have some structure. And finally, I would like to point to a draft FINI T2TRG inter-network. This collects some interesting experiences with running current IoT MACs in the vicinity of each other. There are some surprising results there, so have a look at those. We had about 10 other topics, so I'm not going through all of them. But security, of course, is an important point, but there are also issues around APIs. For instance, how do good APIs for constrained implementations look like? How are we going to do crypto in this space? We will talk about crypto in a short while, but about symmetric crypto, this segment in Berlin was about asymmetric crypto, and also some implementation aspects, like how do you actually talk to a development system? Can you actually do all of your work over one UART? So this was an interesting meeting, and I'm looking forward to meetings like that in the future.
Okay, and I'll give you a quick update on the OCF T2TRG meeting that happened on the Friday before the IETF. So also there, we had a very packed agenda, roughly 16 different topics in 160 minutes. So these are the key items that we had on the agenda, starting with the usual status updates, what's happening in OCF, what's happening at the IETF and IRTF, and really making sure that we are aligned on process-wise and specification-wise and see the same direction there. In particular, we're discussing security topics, OSCORE, the object security work done in the core working group, also MUD, the manufacturer user descriptions, and how the ACE framework could be used together with OCF. Another topic area was the RESTful interaction. So OCF is heavily using links and collections and how those can be interacted in a proper RESTful way. And in particular, one topic was this atomic measurements, how those should be handled. Then there's a whole topic area in ubiquitous connectivity and discovery, in particular how mesh networks and core resource directory can be used together, how you can span across multiple segments of mesh networks and still be able to use the kind of infrastructure that we're building here at the IETF. Also discussed quite a bit on the cloud aspects. What is the IETF view on cloud, what is the OCF view on cloud, and how those things can work together. And then finally, NAT traversal. So if you are behind a NAT and also your other endpoint is behind a NAT, how can you still get a connectivity in between? And then there's a whole bunch of dependent IETF perks. So OCF is using heavily IETF specifications, for example, co-op TCP and also the WAPSAP broker. So those were discussed how we can best progress them. And in that context, we were also discussing the Yang push work that was just presented also in this IETF. And finally, the protocol negotiation work that is going on the core working group. So how can you use different kind of protocols under the co-op protocol? And then OCF has their data model repository, 1IOTA, and it will be very good to get IETF reviews for those models. So we discuss how we can have a pipeline and notifications for new models happening in that area. So we got a whole bunch of action items there. So these are the items IETF and OCF will be working together. So first of all, as Karsten mentioned, we'll be having monthly calls, roughly one topic per call. Those will be announced. I guess we're going to be announcing them on the RG list once we get the exact dates set. Also, OCF is using the resource directory, and the resource directory is now maturing at the IETF side, so they promise to do good reviews on that. Okay. This microphone seems to be going on and off. So yeah, let me know if you can't hear in the back, but then we should do something about this. Then also design patterns for cloud rendezvous. So usually use cloud for finding different devices and what is there are different ways of doing that, and what are the design patterns we should be following to have similar ways of doing that across different organizations. And also in the context of NAT traversal, we discussed TERN, which is a relaying protocol used by ICE NAT traversal protocol. And perhaps we should have some operational guidelines, in particular how TCP and TERN should work together. And then, as I mentioned, the 1IOTA model reviews, so have some notification system that when there's a new models that we could be reviewing, have those who are interested in reviewing them, easy access to them and easy notifications. Then on particular topics for the monthly calls, so deep dive on how to use ACE. So ACE was discussed at the meeting, but since we had only very limited time, we agreed, okay, we need to have a closer look at this and go down to the details. Then how you modify link collections. So as I mentioned, OCF is using links and collections a lot. And how, for example, is there patch format or different formats needed to be able to interact with the link collections in a RESTful way? Also, one topic was this privacy and security related. So in OSCORE, you are exposing some of the headers for middle boxes. So if you want to prevent things like traffic analysis, you maybe want to actually tunnel your object security. And what is the best ways of doing that? What are the right design patterns and alignment? Then there's a whole one topic of atomic measurements or atomic resources and how you can perhaps forbidden by definition or policy access to certain parts of a resource, have them only as a bigger batch. And also how, for example, Coral and HSM could be used for this, how you bundle a set of resources together. So we didn't have conclusions yet on this, but we'll be working on the topic to figure out the right ways and guidelines for that. And one also particular topic that popped up was this, how you re-rendezvous when a co-op server knows that something is broken. So client can, of course, always initiate a new action when it knows something went wrong. But if only server knows something went wrong, how do you actually tell that to the client that something should be happening now? And finally, of course, since there was quite a bit of dependent work happening at the IETF, yes, making sure that we will publish those, that OCF can be using them in at proper time. Then the other meeting, what we had on the weekend was the Wishy Hackathon. So we had a 2-hour session on Sunday. There, the topics that we were discussing is in particular IoT schema org, Ipsos, Smart Object, and OCF models. how can those work together, how we can enrich with semantics these models, that we can make translation and interworking of different models easier. We did identify a set of relevant resources, for instance, the QUDT, ontology, SOSA, SSN, that we'll be having a closer look on this activity. Also, we did discuss that there are a lot of ontologies out there, but do we need something more to glue those together? Is that a glue ontology, or is some other mechanism better? Should, for example, the W3C Web of Things thing description work? So what kind of role should that have be there to be the glue in between different kind of systems? So as Carsten mentioned, we'll be having a follow-up call. It's going to be on Monday, November 27th, 7 a.m. West Coast time. So you are more than welcome to join that. Particular topics that we already agreed for this call is to have a practical experiment. So we will take one Ipsos smart object, probably the temperature object, and we'll define using the QUDT vocabulary, and we'll do OCF and IoT schema org like definitions for that object. And we see how easy that is, what needs to be done more to do that kind of things automatically, and how we can make these things work together. Also, in general, the topic of metadata. What is the right design patterns for having the metadata for your object models and data models, and how to make those work together. So that was the meeting reports. Any questions, comments? Okay, then we can move forward. So next we have Bob Moskowitz with a report on small crypto for small IoT.
Can I have a question? Ali Karimi, you mentioned a lot of organization. Have you guys contacted ITU? Because they're going in towards the IoT's securities. And they are actually, I look at all the areas of the different standard bodies or organization. ITU is ahead of all of us.
Yeah, I think we haven't had ITU persons in our previous meetings. No. So definitely would be interesting to have. Are you
active they had there? In Buenos Aires, they had more information about the security IoT than any other organization I've seen so far.
Okay, so definitely would be interesting to have more interaction with them. So what do you think is the best way to get them involved?
Well, get a hold of the ITU. They're doing that on 5G. I mean, actually, I noticed a couple of organizations, they're building their products based on the ITU standards. Mm-hmm. Yeah, and blockchain. I mean, as far as the security of that, they're using blockchains on the 5Gs.
Okay, thanks a lot. We'll have a closer look at that.
I will send you some info.
And if you have good ideas how to get the right people involved,
right,
please let us know.
Thank you.
Thanks.
Some information, and I posted it to the chat.
Okay. Which chat? The Jabber?
Yeah, the Jabber. Just there's a IoT security initiative from the ITU, and I posted a page to it, link to the page.
Okay, thanks. We'll have a look at that. Oh, and speaking of which, I guess we're actually missing a Jabber scribe right now. Is someone in the Jabber chat room and could be scribing and relaying comments from there?
I can scribe except during my own talk.
Okay. That's a new experiment, remote scribe. But yeah, let's give that a try. Thanks, Michael.
Okay. Good afternoon. For those who don't know me, I'm Bob Moskowitz. I've been around here for a while. One of the original, not quite original, but one of the graveyards here. And I'm going to be talking about using Keccak for small cryptography to advance security in small things. One thing I've noticed since Core was just a BOF was the number of vendors who've left this room. Vendors whose devices and technology were too small to do what this IETF has been talking about. They've got up and they have left. So we've been a bit of an echo chamber here. as we defined our classes of IoT devices, and we said this is class 0 that we can't talk about, and well, okay, those people we can't do anything with. What I'm presenting is some cryptographic work, well standardized, well understood, which will bring them back into the room and will even improve for the larger class devices. Okay, I'm trying to get this in advance.
Turn the thing around.
Let me turn around. Hello? I think you got it right. Push those buttons there, right? The arrows, right?
Let me switch
Here we go.
sides.
Oh, no, now it goes all over the place.
The RF environment here at IETF.
Okay, so what is Keccak? And if there's any Belgium hero who can fix my pronunciation, and even though I've spoken with Johan Damon a couple times on the phone, my pronunciation does drift a little bit. So Keccak is a totally new approach to symmetric cryptography. It's called a sponge function. It is a total break from how we traditionally have done symmetric cryptography, the traditional addition, rotation, and XOR that we're doing since when? Since Caesar cipher. So it's a total break. And in fact, it is such a monumental break that pretty much all the current research is built around sponge function research. This is really important change in cryptography. And you can learn more about it by going to the Keccak site, keccak.team. I'm going to be referencing a number of things from that site as I proceed. Importantly, Keccak at its maximum strength, B equals 1600, and I'll be talking later what the variable B is about, was selected for SHA-3. This is what SHA-3 is, FIPS 202 and special pub 800-185 is Keccak with B equals 1600. At this strength, Keccak is well optimized for 32-bit and 64-bit processors, for multi-core CPUs, for large messages, hash tree evaluation of messages, some really neat high-performance things, which is why Keccak was selected for SHA-3. It's also the basis of the Keccak cipher in the Caesar crypto competition. The Caesar crypto competition is looking at the next generation authenticated cipher. And Keccak is one of the participants in the pretty much the final efforts in the Caesar cipher. And I'll be talking more about Keccak as I go along as well. So this is what Keccak is very generally, and we'll be diving now into this. So the obligatory picture. What is a sponge? A sponge has an absorbing and a squeezing portion to it. And that's why they call it a sponge. There is an R and a C here, and we'll be talking about R and C is. And notice how they're joined together in this picture. That's going to be important in one of the later slides discussions. Your message comes in to the pad, it goes to the function, and it's absorbed and then squeezed, and out comes Z. And this picture is taken from the URL PDF you see here, which goes into really explaining what Keccak is about. So you can go there and get more details. This is one of my two obligatory pictures to show you that this looks really a lot different than any pictures you've seen for AES or SHA or anything else. It is really presented differently. The theory and the math behind it is different than we've dealt with before. One of the most important aspects of Keccak to me is it's a complete symmetric cryptographic solution. It supplies the cryptographic hash. It supplies the keyed hash. It supplies your pseudo-random function. And it supplies your authenticated cipher. All four major things we need for our symmetric cryptography. So in a single primitive to implement, it replaces AES, HMAC, SHA-2, go on down the list. One hardware component instead of multiple components you may have to put into hardware to improve your performance. So it is one underlying primitive to give everything. This is important in terms of code size. Now, let's get a little bit into Keccak. It's highly parameterized, and it comes in all sizes. So B is the width, and B comes in sizes from 25 times 2 to the n. So you can see 25, 50, and so forth up to 1600. Where the 25 and 50 are toy sizes that you can sit down with a piece of paper and pencil and come to an understanding how Keccak works. It's when you get to 100 and on up that you start getting to some meaningful crypto. Keccak defines a bit rate R rather than a block size. And I'll try to explain this without getting to depth. And what we have is we have three variables, R, B, and C. So B is the width. And so what is R and C? C is the capacity, where if you want a strength of n bits, the capacity is 2 times n. Remember that picture before? We had R and C together, which shows then that's B added together. So if R equals B minus C, then B equals R plus C. Thus, if I take B equals 400, and this is really important, I can deliver 128 bits of proven strength with C equal 256, and thus R equals 144. And what this basically means is we're operating 144 bits at a time. That's what the bit rate means. It's kind of like a block, but it's not a byte block, it's a bit block. And this is really good for small messages. Kind of multiple rounds for a big message, but it's really nice for small messages to have a small R value. Another important parameter is the number of rounds in Keccak. Keccak defines 24 rounds. There's currently published attack against 6 rounds. Because of the parameterization, if the attacks start getting better, you can increase your number of rounds with the according performance hit to significantly increase the strength of Keccak. So it is future-proof, considered future-proof against unknown attacks by the fact that the rounds itself is one of the many parameters in Keccak. And you could reduce the number of rounds if you're trying to get better performance and not too concerned about whatever attacks may be coming along. So this is a little bit about the parameters and understanding of Keccak. Oops, it's back up there. So again, Keccak with the block size of 400 is very well tuned for truly constrained IoT. As I said, R equals 144, well suited for small messages. You're processing 144 bits at a time. Your messages are small. You have very little padding to do to get them to work into that block size, and in terms of how you have to feed things into the sponge, etc. In most cases, 120-bit strength is more than adequate. I know people are saying, well, what is quantum computing going to do, and what is NIST recommending for 2030, and some of the rest of this. We can get into all sorts of fun discussions in terms of crypto strength. We can also talk about how much electricity it takes to break a single key by brute strength. And so right now I feel quite comfortable saying 120 bits strength is more than enough. Shake 128. Shake is defined in FIPS 202. So Shake 128 is kind of thing derived from it. If you base this on B equals 400, in 202 it's B equals 1600. But instead we're decoded for 400. It's just like SHA-2, but a magnitude faster. This is a magnitude faster than running SHA-256 on straightforward coding considerations. And I've seen numbers even better than that in some of the discussion. KMAC, which is the keyed MAC version, also in I think that's in Special Pub 800-185, outperforms HMAC with smaller code size. It's a single pass instead of a dual pass, and it's using Shake 128 instead of SHA-256. You can do the math. It comes out much, much faster than what you do for HMAC today. And finally, Keccak Senior outperforms ASCCM, again, in at least a magnitude better performance. And it is a 4-byte block, and it produces an 8-byte tag. Again, very well suited for a small message. Yes, you can have larger blocks in your output, but it's working on a 4-byte block orientation. Keccak has a whole class of sizes from Keccak Junior to Keccak Major, which is 256 bits of strength and big messages and so forth. So that's why it's a full class solution coding. And again, another obligatory picture. You have what's called the duplex construction, which is how we can now take this hash and turn it into a stream cipher that we can now take in a block and put out a crypto block and proceed along. So, and actually it's reversible. The duplex construction goes in both ways. Not only is it one direction for our cipher, it's the other direction for our perf. So again, it's almost like one block of code doing the two different things. To wrap it up, I feel in many ways that I kind of missed the boat on this because it's been around for a while, though Keccak is not so new. And I've only been working on this now for about 6 months, researching and studying it. I have a skeleton draft out right now. I have a lot of pieces. I got to, how to take all of the tables that are in PDFs and put it into internet draft format to show the performance and the security items. So I have a basic draft out, and it's a work in progress of getting to the next round of getting all of the actual performance numbers and the actual security considerations and why this is worth doing into the next version of the draft, which I hope to get out before this year's out. And there is a significant amount of open code which exists on the Keccak team site, and also hardware design as well, open hardware design. So my next steps is to advance this draft, and now then to specify Keccak with B equals 400 for IPsec, HIP, TLS, the CBOR concise identity work that we have coming along, and then develop into the IoT devices. One thing I'll say here also that I didn't mention is that if you've looked at movement on asymmetric cryptography, and if you looked at EDDSA, and you get into looking at the EDDSA RC, and ED25519 specifies SHA-512. So kind of, well, that's kind of hurts for doing that in small devices. And historically it was because that it should probably be Shake 128, except that ED25519 was done prior to the publication of FIPS 202. Whereas ED488 was worked out after that, so it does specify Shake 256. So if you wonder why that RFC's got the two different things, it's a bit of history. So one of the things that I'm also going to be doing is working on an addendum to EDDSA to use Shake 128 and to allow to using Shake 128 with B equals 400. So we'll have a digital certificate as well tuned as possible for highly constrained devices. That the hash we'll use is one which runs very efficiently in these small devices, along with the EC25519. So these are all areas where that is on my docket to do. I'm looking for partners who want to work with me on this. And in terms of standardization, NIST looks to what the community wants. If the community says that, this other stuff which is out there and well studied is what we need in our product, NIST does listen. But if nobody comes up and says, we really need something, they're really busy on doing reports to Congress on things like on botnets, stuff like that. So if we want to get the resource and attention, we need to come forward with the documents, with the products, that show that this is why we need this in our industry, and they'll listen. They will listen to us. So that does complete my slides and presentation. Maybe gone a little bit fast and maybe not as deep in as you want to, but then I don't consider you as a bunch of cryptographers are going to beat me up. I do got my Kevlar suit on here, and I'm ready to take comments.
We have about 10 minutes time of discussion.
Okay. Gabriel Montenegro. Yeah, thanks. Very interesting. So this is not very, very well known, which is usually not something good for crypto. Any reason why this shouldn't go? Well, okay, the existing model, as I understand it in the IETF, is for crypto stuff, we have the CFRG, and they serve as sort of a consulting body. Maybe they can look at this and, basically come out with their opinion on whether it makes sense in what scenarios, whatever. Because potentially, if it's really good, it should be useful not just for IoT. Hopefully, if it's really good, it's useful in other scenarios as well for other types of devices. So one thing I would encourage is for CFRG to have to state what how they see Keccak, and then the model is in the IETF. Other groups then take the information and the guidance from CFRG and then apply that in standards track documents. They just inform, do informational stuff. But would that model not apply here?
I'm going to be taking this to CFRG.
Okay.
That's going to be happening. I want to get a little bit of interest, saying this. There are people who do want lightweight, faster ciphers, so that when I take a CFRG, I'm not just saying, well, here's yet another cipher, but I want that I'm saying that here is where the interest lies for this. That's there, and yes, it's we kind of missed it with all the tension on the bigger use of Keccak, which was SHA-3, and missed its viability for this. And as far as in other areas, well, consider the router vendor says, I can't possibly encrypt my IP fixed flow because I don't have the resources to do ASGCM on it. And now, here is a way that you can protect your IP fixed flow, and other sorts of things. So I think this is a good audience to get the discussion going, and then it can cascade out from here.
Ali Karimi, what is your vision? Is it your vision is centralizations or decentralizations? Because when I look at this, I look at the big data, and big data is not an enterprise anymore. And where are we going as far as Keccak? Is it centralizations or decentralization? Because if you look at the use case of the healthcare comes in as a patient, I can direct who can get my file, who cannot at any moment. And where do you take this as far as the topology and centralization or decentralizations?
The sensors start in collecting that data. You have a pacemaker, which is sending data back to the hospital, which ends up getting into the big data. But for HIPAA compliance, you had to protect that pacemaker communication from the pacemaker over a potentially non-IP network because of in-body requirements, all the way to the hospital. And you have to do it in such a way that you're not having to replace the battery on the pacemaker, which means surgery, more often. So having something like this for that end of it. Yes, big data, how you protect big data, how you do field protection, the rest of it, that's a whole nother discussion. What I'm focused here is that what is the security we use in our communications, not in how we necessarily encrypt the data at rest.
I understand, but you used to do looking at design the application, then design the network, and design the security. The world is coming in vice versa. Now we design the security, then applications, and the network. That's how it's going to go from now. It used to be vice versa. Now it is security comes in first. That's why I ask you, you're looking at the centralization or decentralization. Based on the healthcare today, even in US or Europe, it doesn't go into one locations anymore. I can choose to go in my information to multiple sites, multiple countries, and multiple physicians and nurse practitioners or nurses or anybody else's. Then it's not going to be in one hospital.
If I want to look at protecting data at rest and using symmetric cipher for doing it and having performance so I can pull that data out quickly with all the rest of my process I want to do, I would want to have the lightest, fastest cipher that I can find that delivers security. Unless I have to do format preserving encryption, which is another class of discussions, and doing column-based, if you want to have that discussion on big data protection, we can have a discussion on big data. And yes, all those things have to be done. But some of these discussions get very orthogonal when you start talking about the actual cryptography involved.
Don't get me wrong. I like your approach, but we got to look at it. How are we going to drive this?
There's not one thing which can fit every piece of this.
Alexander Pelov, thank you very much for your presentation. I personally was not aware at all about the existence of these algorithms. And I think, so my co-chair of the LP1 working group, and I think it would be
The what work group? I'm sorry.
LP1.
Okay,
yeah. And, there we're talking about small messages by default, right, on the radio side.
Mm-hmm.
So I think that this work could be pretty interesting, if you can continue pushing it on and maybe at some point come there and also present it. So I think that could be a good place to also get some eyeballs on it.
Okay. There is a study group that just started last week in 802.15 for advancement for next generation security for 802.15.4. Of course, the why some people want bigger security, they want AES 256, but I'm going to use that as an excuse to get the littler stuff in too.
Mohit, can we have the slides back? I just wanted to ask where you compare Mohit, M-O-H-I-T. So before this, yeah, it outperforms HMAC with smaller code size and the same for SHA-2 with a factor of 10. But at least from what I have seen, IoT devices are, the code size is not always the most limiting factor. How does it compare with RAM and like the memory usage and not the flash? And how does it compare in time, like execution time?
I've seen those numbers in their documentation, everything lower, literally across the board. And it's like two of us are going to have to sit down and work with those tables and what I'm going to pull out and actually put into my draft. So you've just kind of stepped forward. I'll step back around you on doing that. So it is it does take less power. It's using simpler operations, a number of items on that from what I have seen from their documents. And you'll help me understand that, make sure I pull the right pieces out. Anything else? Okay. I thank you for your time, and I please ask you to help me out and get this going in it so that we can bring these people back into the room, and then we can expand out and do a lot of things a lot better than we have so far.
Thank you. So it will be exciting to see this wholesale swap of the symmetric crypto unfold. The next topic we have on the agenda is edge computing, and we will start with one talk here. Who wants to take the clicker? Yeah, just pull it in, plug it in. Yeah, just plug it in.
Okay, so good afternoon. So this is a presentation. Is it okay like this? No.
Okay, you may have to say next slide. I can change it here.
Okay. All right, so this is a presentation on edge computing and IoT. This is a continuation of work initiated by Dirk and Yves and presented in IETF 100-T2TRG. Okay, so, and my name is Xavier Defroy, and I will present on behalf of my co-workers here. So IoT today means handling a massive amount of data generated at the edge, reversing today's dominant data flow. And solutions involve edge computing, either at small scale data centers or further towards the edge. So in this presentation, we'll cover some motivations for IoT edge computing, an overview of major industry and research projects, and the potential areas for future work. And our goal is to gather input from the community, and in particular to identify challenges that are relevant to IRTF and to T2TRG. Okay.
Try now.
Thank you. So the motivations for IoT edge computing, that's basically to support high data volume at the edge, to support highly time-sensitive and trust-sensitive applications, to exploit opportunities for energy efficiency and cost reduction, and to adapt to intermittent connectivity, and also somewhat to open the edge. So that can be expressed in multiple ways. So we have three here, and they are kind of interrelated. You can open the edge by enabling multiple providers to offer competing edge computing services. You can open the edge by enabling open and secure access to data. So data collected at the edge could be consumed by multiple services at the edge. And also you can open the edge by enabling open and secure access to computing resources. So for example, you can have multi-tenancy for third-party applications. So we start the very quick survey here. With the telecom industry related initiatives. So IoT is not the main or the only use cases there, but it's one of the major one. So we start with ETSI-MEC. ETSI-MEC defines an architecture for a mobile edge platform and defines services provided to mobile edge applications, hosted applications. Here we have the architecture from ETSI-MEC with an NFV-MANO based control plane, the mobile edge host, and containing the platform providing the services. In phase one, so ETSI-MEC defines some major interfaces and basic services. In phase two, which started in January this year, ETSI-MEC, basically planned to become multi-access, multi-domain, multi-operator, and basically also more distributed and more lightweight. So, more lightweight, it's not going very far down. It's just having containers in addition to VMs, but more distributed because applications hosted on the mobile edge hosts will be able to talk to each other or be linked to each other in some way. So quickly now we can go through the other ones. You have open edge computing, which offers a cloudlet-based architecture for offloading computations. The Telecom Infra Project, or TIP, as an edge computing project, but TIP focuses on use cases and implementations and not not architecture. Then 3GPP builds in some support for edge computing in 5G. So basically, you will have the possibility to redirect flows towards local data networks, and third-party application function will have the possibility to influence this in an indirect way. MCORD still working? MCORD is basically aims to integrate this 5G architecture into the central office, and that includes edge computing as well. And basically, to conclude this group, you have a research project, 5G Coral, which is a European research project, which combines telecom, edge computing, and fog. So here on this architecture diagram, you can see you have, on the top left, you have an NAV MANO-based control plane again. And underneath, you have this edge and fog computing system. So this is basically a federation of nodes, of computing devices, which can host apps, applications, functions, and services, and different types of programs. And this federation is formed with very different types of devices. You have edge data center servers, computing devices co-located with the base stations and other access nodes, and fog computing devices co-located with IoT devices, mobile phones, and so on. So to conclude, these projects, they are typically driven by the telecom industry. They integrate with telcos network. They are often NAV-based. And some of these projects are evolving towards more distributed computing and more lightweight computing as well. So now we look at the fog model, or the intelligent IoT gateway model. We have products on this page. So you have gateways from Bosch, Siemens, Microsoft, Amazon, and the EdgeX Foundry, which is an open source project initiated by Dell. These are software projects, except a few, like Siemens and Snowball Edge. The Siemens Gateway and the Snowball Edge are hardware products. But basically, they all start from a simple model. They can evolve a bit from it, but mostly that's a single tenant gateway running a pre-provisioned code for data processing at the edge. And if you take a look at the diagram, this is basically the Microsoft Azure IoT Edge Gateway in the context of the Azure IoT system. So you have the cloud on one side, the devices on the other, and the field gateway is used in one of the deployment scenarios. It is used for protocol translation, or other types of computing like analytics. And also this diagram illustrates the use of protocols such as HTTPS, MQP, MQTT, to communicate with the cloud. And you have a range of other protocols used between the device and the gateway, and some are listed here. Amazon, Greengrass, and Snowball Edge, they can run basically AWS Lambda functions, which are stateless functions. And additionally, a Snowball Edge can be used to ship a massive amount of data to the cloud. To conclude this slide, different levels of control can be provided to developers. You can have full control over an embedded Linux gateway, or you can go much higher in terms of programming model. So to complete this group, you have the OpenFog architecture from the OpenFog consortium. It integrates computation, networking, including time-sensitive networking, storage, control, and acceleration. And it is linked to a new IEEE working group, the Fog Computing and Networking Architecture Framework. So it's quite recent, but I believe the current goal is to standardize the reference architecture from OpenFog, and then to go on from that point. This diagram illustrates that OpenFog gateways can be connected in a tiered fashion and also using east-west connectivity. That illustrates a general, basically, trend towards a more distributed fog. So now we look at emerging trends, especially lightweight in-network computing. So we can start with products. Serverless computing products include Cloudflare Worker, which is a CDN Edge product, which can run JavaScript programs, and Amazon Greengrass and Snowball Edge. So they exploit statelessness to decorrelate service from server location. And named function networking goes forward by leveraging ICN to provide a more granular approach. Finally, we have the FLAME, which is another European research project, which transports IP over ICN and basically performs service routing in ICN layer to optimize traffic, especially at the edge. Stateless functions are easier to dispatch to any server, and so this enables advanced data and service routing to be developed. And also ICN technologies support intermittent connectivity and dissemination of local data in a manner less tied to applications. So we'll have an example of this in the last survey slide here. This is basically zooming in NFN. NFN enables accessing static data and dynamic computation results in one single data-oriented framework. Then you can benefit from ICN features, data authenticity, caching, and so on. And also you can enable the network to perform various optimizations. And the network has some tools to do that. The network, when an NFN node receives a computation request, the NFN node can either return a cached result, it can fetch data encode and sends back the computation result. And it can also forward the request towards a more appropriate node. And additionally, it can split the program into subprograms and use any of these techniques on the subprograms. And so one reason why NFN could be well suited for edge computing, for IoT edge computing especially, is that it enables secure access to individual elements within named data objects. I mean, that's detailed within the reference 7, that's in the last slide. And that enables some form of selective access to data elements and even possibly preprocessed data elements. So that makes it possible to preserve privacy, for example, in a way less tied to applications. So I don't know, in terms of time, do I have enough time?
5 minutes.
Yeah, okay. So maybe I will pass over this one. That's just basically a summary of the various the various characteristics of the projects we have seen. And we can move through the gaps. So in terms of IoT edge computing, we see an evolution towards a more distributed computing model. And also we are in a context where the network is dynamic and constrained. I mean, the environment is dynamic and constrained. And so we get a lot of challenges from this because to solve. Because, for example, you have challenges on creating local cloud federations in these dynamic and constrained environments with protocols to declare availability, status, capabilities, association. And also, you need to answer the question, where does the control will live in that situation? You have challenges on creating clouds of clouds, which can find and help each other, share resources, and make themselves available for federation, and so on. And you have challenges on operating those edge clouds in that dynamic and constrained environment. So determining an optimal placement for caching and computing, considering service acceleration and other resource capabilities, and doing the associated routing of data and service requests. So IoT edge computing also evolves towards a more open model. And so you get a new set of challenges that could derive from this. So challenges related to open access to compute and storage resources. So you, for example, you may need to have generic APIs for developers to ask for resources meeting specific requirements. Also, you have potential challenges related to open access to data, to liberate data from silos. So again, you could have some form of APIs there, for data and metadata lifecycle management, access control, auditing, managing impact on privacy. And then you also have challenges on multi-tenancy, so providing fair and secure allocation of resources to tenants. And finally, IoT edge computing also evolves towards some lower-end devices. That's kind of related to mist computing as defined by NIST here. And that may require dynamic and lightweight cooperation of things, edge devices, and compute platform. So this evolution can also increase the challenge of QoS at the edge and may require some form of dynamic network slicing as well. So to conclude, we have reviewed technologies related to IoT edge computing and looked at potential gaps. So now we are seeking help from the community to gather more input and to brainstorm on what the IETF should do. So is this the right research group to work on these topics? And what challenges would be most relevant to that group? Oh, yeah, there is maybe there is a follow-up meeting, so maybe Dirk can mention that.
I'm Dirk Kutscher, so co-author of this. So this originated from edge computing discussions in this group, like in the previous two meetings, I think. And so the general idea was that so there are all these existing telco-motivated edge computing approaches that Xavier presented, but they are normally operating in a way where you extend, say, cloud-based or data center-based edge computing to some point in the edge. And so the thesis for this work was that so in a, say, thing-to-thing environment with constraint
closer
nodes.
to the mic, you're hard to understand.
In a thing-to-thing environment with constraint nodes and a, say, distributed communication and computation model, you would have a different requirements. And so if you are interested in discussing this more, so we booked the Butterworth breakout room tomorrow at 3:30. So please come to me after the session if you are interested.
Can
you
announce that to the mailing list so people know? Okay.
Eric Nordmark. It was actually quite useful to have this sort of overview. But one thing that might not be research, but is, I think, a practical consideration as you start doing this is our good old friend NAT traversal, right? That once you want to enable east-west communication at the edge, you don't have to go that far before you'll find that there's a NAT between the different devices at the edge. And that might just be an engineering question. I mean, in the IETF, we probably have half a dozen different ways of doing NAT traversal, but I think it's one that we shouldn't lose track of in the bigger picture. So the other ones that I think that, so there's this other proposed research group with Dirk with DIN-RG, right? Basically looking at how can the edge actually be more independent, more autonomous from the rest of the internet, and to what extent can you do naming and security and whatever in that context? And I think that that's an area where there definitely is research that needs to be done.
So yeah, quick comment on Eric. So Ari without the hat on. So yeah, NAT traversal, certainly we have the thin ice activity already on that. It would be something interesting to explore, whether that's the kind of solution what we want. Do we want something else, and how to really solve these issues? So also very much interested in the whole problem space. Okay. So head back on. We also have another presentation on the IoT edge computing topic. Roughly 10 minutes to go. We're gonna squeeze in our our last slot a little to be able to make it also for the demo.
Very good. So while that's being queued up, Mike McBride, I'm here in behalf of Mr. Liang Gang of China Mobile, who has a conflict right now. And so about 10 minutes should be okay?
Yeah.
Okay, so 10 minutes. Yeah.
So still fighting with the technology, sorry?
Yeah, no problem. I can talk without the slides. We've been coordinating with the previous presenters, Xavier and Dirk, and we have a more narrow focused aspect of edge computing that we've put into a draft. The authors, Martin, Remy, myself, along with Mr. Liang, are very involved in industrial internet forums, particularly the IIC, Industrial Internet Consortium, and others as well, including ECC. And so our focus is very industrial focused, and it goes beyond the traditional access network portion of edge computing and pushes it a little bit further, or a lot further, depending upon your perspective, to on-premises, particularly in factory settings, directly connected to factory equipment, whether it be elevators or windmills or whatever it may happen to be. So we have this problem statement that we've created. So that's a little bit of the background. We held a side meeting last IETF to discuss these potential use cases. We created a problem statement, and since the last IETF and this IETF, we've created this problem statement draft. And like the previous presentation, we did mention other work going on in other forums, because edge computing is kind of like cloud, where it's spawning everywhere. A lot of people are talking about it, a lot of debate about what edge computing, the definition of it and all that. So we're not really getting into that. We're trying to keep it focused. What some of the things that have come up with the discussions we had in the side meeting and that we've put into this draft is things which was mentioned in the previous question, is that, you know, maybe there's a existing or a need for a new protocol for east-west communication between multiple far edge or beyond edge computing or beyond access computing gateways. Perhaps there's a common API that's necessary between across edge compute platforms. User mobility is a potential area, edge-to-edge mobility. We don't want to duplicate effort that may be happening, for instance, in ETSI's MEC group. So we would need to evaluate whether that's necessary or not, maybe an autonomous vehicle setting, or maybe virtualization of VMs or containers from one edge device to another. Edge device configuration and management, lightweight virtualization technologies. Security is huge as well. That's one of the main concerns in industrial settings, is on security, which is one of the main reasons that they haven't wanted to open it up to the internet. And here's the draft. So I think you probably get it at this point, the focus of our draft, just to kind of visually depict it. On the upper part of this diagram, in the yellow part, you have your core data center, regional data center, access network. And again, typically edge computing topics, whether it be, CORD or other types of proposals, are typically focused on the access network side. And what our focus is more on the on-premises side of a factory. The component of edge computing could be actually placed on top of an elevator, for instance, or directly connected to a robot in a factory. It's that proximity to the edge that is where our focus is. And we have a little bit of technical difficulties here, but again, I can keep going if we need to do so without slides. Okay. Thank you. All right. So there's a variety of verticals within the industrial sector. We focus on some of these use cases, some use cases specifically. And again, it's tempting at times when we meet together to, have feature creep, but we're really trying to keep it focused, which will be more successful. If eventually it does go towards becoming an IETF working group, then we need to be focused. So some of the capabilities of beyond edge computing, or whatever you may want to call the topic that we're discussing here, is heterogeneous IoT device capability. There's a variety of interfaces on the IoT side. Zigbee, Wi-Fi, lots of different industrial field bus technologies, frameworks, and protocols that are being used. Needs to have low and deterministic service latency, data preprocessing and traffic offloading, system resource isolation, being able to support multi-tenancy situations, and offline processing as well for robustness. End-to-end security, again, is paramount. Maybe even potential topics would be distributed AI, making use of GPUs and TPUs for AI applications. Real-time operating system, for instance, industrial Linux for spontaneous events. Perhaps a unified API for multi-ecosystem edge application. So there may be some API work needed to be done there, and perhaps some service isolation for network slicing, mapping services to specific network slices. And again, with even all those, again, we're trying to, pinpoint maybe a particular, just one of those that we'll focus on as part of this effort. Please look at the draft, but this just kind of gives a high-level look at the overall architecture. You've got the Beyond Edge Computing Management Platform with application management, device management, resource management, and even an SDN platform as part of that. You've got your separate IoT cloud services. So you get your management channel and your data channel going into the BEC node. That data channel needs to be able to support industrial frameworks and protocols, as was mentioned in the previous application, including frameworks like DDS and OPC UA and things like that. That's important. And we need to be able to provide a distributed BEC platform and a unified API. So this is just an example of an end-to-end BEC system where you've got factory equipment on the left-hand side connected using serial interfaces or, Profinet or some other type of industrial protocol, connected to a edge gateway on premises, and that gateway includes applications, and it may include a, instance of a cloud software for being able to offload certain functions to the cloud where necessary. In this case, it's GE's Predix, but it could be really anything. In the IIC, the Industrial Internet Consortium, as I mentioned, it's very testbed focused. So there's, 30 or so testbeds around the world focused on certain aspects of industrial internet, where you've got vendors of networking gear, and then you've got vendors of industrial equipment coming together to do some test beds. And in this case, we do have one, and we highlight this use case in the draft with regards to elevators. So in this case, we actually have in Nanjing in our open lab a mock-up of a elevator, a mini elevator by Schindler Elevators. And on top of that, we have a edge compute IoT gateway and a connection to a server, which is running GE's Predix. So this is kind of our goal, to continue to expand this, to include other edge gateways from other vendors, to be able to do some interoperability testing. And maybe we'll find that there's protocols that work fine, or maybe we need to develop some new ones. So just quickly, so gap analysis that may be done in the IETF. I mentioned some of these earlier, but perhaps multiple virtualization technology, coexistence and coordination interface model that may be required for between various virtualization technologies, a lightweight device level management and virtual resource, framework and APIs for multi-ecosystems and runtime updates. So just inclusion, last slide. So our methodology has been that, distribute as much as you can and centralize only if you must. This is a very popular topic. We're trying to keep the topic narrow in our particular draft. There's some interesting things that are happening in the industry. Some of the ones that I'm just being made aware of recently is like Open Industrial Linux, OpenIL, which is interesting. And there's security efforts going on here in the IETF, including the suit BOF, which is could be very useful. Maybe we'll find that some of the things that we develop security-wise may be contributions into that effort. We too are having a BOF, or not a BOF, a side meeting or bar BOF, if you will, this Thursday. If you have something specific that you'd like to contribute, please feel free to attend.
Ali Karimi, you're talking about industrial area, like any industrial area. Are you thinking about how they're going to migrate from their existing protocol, BACnet? Because most of them, if you go to the elevators, you go into the electrical grids, all of them, they do have BACnet. And it's very tough to migrate from BACnet to IP. It's being challenged for past 5 years. And I know a couple of guys from the IETF, and we tried. First, we got to look at that step, then migrating to others.
Yeah, there may be some comments to that. That's kind of a broader question, but my answer to that would be through partnerships. Vendors of networking equipment, like I mentioned, working with industrial players, like that's the only way that we've been able to make it work. And we do have, as a vendor, partnerships with elevator companies. And so we're able to take sensor data, put it into a edge compute device, kind of out of band, actually, which won't affect their existing industrial equipment. Dirk.
Dirk Kutscher. So, I mean, this is currently happening. So there is a huge, not migration, but conversion towards IP technologies in industrial IoT. And so why this is so relevant is that, all the automation companies and so on, so they are currently using their own, homegrown proprietary computing frameworks to distribute data and to do analysis and so on. And so this is going to be a security, potentially performance, and into our problem in the future. So this is why this is so important.
Eric Nordmark. So your previous slide, you had gaps, and I was trying to understand the virtualization technologies. Are you talking in general about compute, storage, network, or specifically about network virtualization technologies?
I believe Mr. Liang in this case was, in this the way that I would interpret it would be, there's different, as I mentioned, there's different verticals within industrial, whether that be oil and gas or whatever it happens to be. And for within those industrial settings, there's certain apps that only work in those industrial that aren't, they don't work in any other industry. So the goal would be eventually to virtualize some of those applications, and maybe there would be a certain interface model necessary for those particular verticals applications. That's the way that I would take it, but maybe there's a broader.
But that's sort of a step removed from, what does the IETF need to do here? Because that sounds like it's more about, how do I virtualize the application, maybe break it up, how do I deploy it out at the edge, right, in a virtualized way, which is separate from how does it communicate over the network in a virtualized way. But
yeah, that's very well. Good comment. Yep.
Hi, this is Eve Schuler from Intel, and so I've been part of the dialogue the last couple of IETFs about edge computing, and was part of the discussions that led to the previous presentation. But what I wanted to emphasize, I love these gap analyses. I love that we're looking across all of these different groups. Many of them are focused on frameworks and architectures, and all of that's good. I think what the IETF does really well is the specification of the communication protocols between the components in these architectures. And I think that that's what's missing from many of these other conversations. And so the question to you and other people interested in this topic is really, and would be part of the conversation on Thursday, and the follow-up would be looking at this ecosystem of components. Where are the places that we can design communication protocols between those components that'll sort of push the architecture to be real. And so the gap analysis, I'd love to move that conversation towards what are the things that the IETF does really well, whether it's service discovery or federation of things, or or routing protocols that are data centric for caching in the network. So that's one point. Is this is really a question for the community. Can you identify and prioritize what are those gaps that relate to the communication protocols? The second issue to point out, and this is in contrast to the previous kinds of presentations that were and discussion around constrained IoT, is that what's quite interesting about edge computing or edge and fog computing is that it shifts the discussion of the IoT away from exclusively about constrained devices, because now you're moving fog and edge functionality to the edges of the network. Those are not necessarily constrained devices that might help with that sort of functionality. And so I would also challenge this group to think about the kinds of functionality to be supported in the IoT that supports not constrained devices, that might be the orchestrators or the aggregators of information and control. So I think it shifts our discussion here as well. 2 points.
Thank you. Very good points. And we intend to follow up from the problem statement draft that we have with a gap analysis draft, which would be helpful to your point.
So I need to close the mic line.
Dave Taylor. So just to comment on the discussion around BACnet and migrating to IP, I think Dirk had a good slide in the presentation that showed a protocol gateway, right? And so that's what people are doing right now, even with BACnet, right? You're on BACnet on one side, and you use the protocol gateway in the diagram to talk to something else, right? And so I think this BACnet is, of course, not the only case for this, right? This is a common problem, and that's exactly why we have protocol gateways in such architectures. So.
Matthias Kovac, Siemens. So I'm still trying to wrap my head around kind of what is your starting point, what concepts you already have there. I saw quite some parallel activity to what is happening in the Web of Things at the W3C. So we have quite of the features you were looking for. And I think it's also a good group, because it takes the concepts from the IETF and tries to combine it to something that is application facing, which in this case is the industrial approach. And we have, I'm from Siemens, and we have other industrial partners in that group. And we for instance, have already running demos that combine BACnet, Modbus, OPC UA, and these things, and bridge it, and try to kind of harmonize this gateway approach so that there's a common uniform language to describe and have a better deal with all these different gateways that would be needed. So
that's
maybe look into that.
The working group that you mentioned at the very beginning of your comment?
So it's in the W3C. It's called the Web of Things activity. We have an interest group that does exploration work, and we have a chartered working group that already standardizes the first building blocks that we're using to kind of do exactly this kind of really complex, big ecosystem to enable application-facing solutions over different platforms in the IoT.
Awesome. Thank you.
Okay, thank you. And now for something completely different. Matthias talked about the W3C Web of Things group that actually met last week at the W3C TPAC meeting. And there was an interesting demo about Web of Things and semantic interoperability. So Michael, can we hear you?
Sure, but could you grab my latest slides? I emailed you about an hour ago. I can use these, but my latest ones are a bit improved.
You sent us new slides?
Yes, about an hour or two ago.
Okay, give us a second. Maybe you can just start talking.
Sure. So basically, last week was TPAC, which is W3C's semi-annual general meeting, and the Web of Things working group, which has been working on combining IoT standards with web standards, and in particular looking at metadata for IoT devices and how to describe them, had a Plugfest as well as a working group meeting. And so that group, just mute my speaker here, hopefully you can still hear me. So that group met, and we had a plug fest, and we also had, of course, a standards meeting. And what I wanted to show you here was basically a report out of the various topics we've worked on. And so the plug fest, we actually looked at a couple interesting topics. I myself actually looked at the problem of semantic interoperability. And we actually had some pretty successful approaches where we combined some web technologies for semantic interoperability with some IoT technologies. That's the right slides. Let's proceed to the first one. So this slide deck is a little long for this context, so I'm going to go pretty fast, but of course you can look at the slides later on, and there's hyperlinks and such in the slides as well you can follow. But basically I want to talk about, what is interoperability, and in particular what is semantic interoperability. I want to talk about, some motivation for this, and then talk about how we actually implement it. And I also want to walk through, the test cases we did as part of the PlugFest at the web. Okay, so next slide, please. And this is in the context, by the way, of a concept that we've been calling ambient computing, which is, right now we have devices that are kind of, relatively limited in their connectivity, either vertically or horizontally. And we have a lot of problems, going east-west and this sort of thing. Eventually, we want to integrate the concept of fog computing into edge computing. But even right now, the definition of fog is pretty, constrained to services running on fixed nodes and not able to move or anything with this. I think in the long run, we want to look at mobile services that can be in the cloud or in the fog, that can migrate around, that can come and go. And we'll have to worry about discovering them and managing them. And so in the long run, we're going to need a lot of stuff to make this all happen. And we're just looking at small pieces of this. Next slide. Okay, what is interoperability? There's quick definitions here. So basically it means you can plug things together and they work, right? So, and that's a simple definition, but there's lots of examples of this in the standards. A good example is I can replace the light bulbs in my apartment, and I can go out and buy a bulb and plug it in and it works. And this just works. It actually takes a lot of work behind the scenes in standard setting. And so for the IoT, you want to accomplish the same thing. You're able to take a device and have the devices from different manufacturers, and we just plug them in the same system and they just work. So how do we do that? Next slide. So there's different levels to interoperability. A lot of the work at IETF is down at the even lower level than the three mentioned here, at the level of protocols or communication. But at the level above that is once you have the data, in the payload, you have to decode it. And there's kind of three levels to that. Syntactic is, I got a bunch of bits, and I turn that into somehow, some serialized data, and I turn it into a data structure in memory. Great. The next level above that is structural, which is, I have this data structure, but I want to organize it. I want to turn it into organizational patterns. So it's a list or an array or a set, or it's enumerated types or numbers or whatever. So I have these sort of primitive types, and they're organized according to some patterns. And that's structural interoperability. The higher level above that is semantic. So I got a number, I want to know that it's a unit of temperature in Celsius, and it's actually associated with a certain sensor in a certain place, taken at a certain time, and I can relate that to other sensors. So semantic interoperability is I want to get to the level where I actually understand the data. Now, it turns out that structural and syntactic, if we use things like XML and JSON, they're sort of self-parsing. And so the structure is sort of embedded directly in the standard. And so that we have a pretty good handle on that now. So now we got to deal really with how do we handle meaning. Next slide. Okay, and then finally, this motivation issue is why do we want interoperability? I keep getting asked this. It's kind of the whole point of standards. So let me just address this. Basically, it's the money. So a lot of assumptions of the value of IoT assume things interoperate, right? And actually, you can pretty much cut in half the value of IoT if you keep things trapped in silos. And now this thing actually said, 40 to 60, it varies by area. It turns out that actually home is not the place where interoperability matters the most. It's actually the factory where it matters the most. So the home, it's only worth 17%, but in the factory, it's worth like 60. So interoperability is very important, and especially in more industrial use cases and institutional use cases. And this is basically the cost of the integrator to put systems together grows dramatically if things are not interoperable. And next slide just shows you, the scale factor and also the changes in the various areas with those scales. All right, let's go on to how we do it. Okay, so there's a couple of projects. Next slide. So a couple of projects that we've been working with, and so one thing to do semantics, you need to have a common vocabulary or a set of terms. And so there's been a project called ioschema.org that some people I know in the room are involved in. And this is basically an attempt to define a simple common vocabulary for the IoT. And it's actually associated with several other projects, including RF and SSN. But it's a nice, straightforward project, and I think it needs more attention. But we attempted to use it in a test case during TPAC. Next slide. And this is just a basic idea of what it looks like. Basically, it divides objects or devices into a set of capabilities. And then every capability has a set of interaction patterns that can have actions, events, and properties. And this happens to map very nicely onto the interaction pattern model of the Web of Things. Next slide. And then notably, things themselves are considered as sets of properties. So rather than trying to define an ontology for entire devices, which is very difficult because devices can overlap significantly in capabilities, and even similar devices can have slightly different capabilities, it's better to just focus on the capabilities themselves and then think of devices as sets or bundles of these capabilities. And that's the approach kind of taken with IoTschema.org. And this allows you to actually model new kinds of devices as long as they're just combining existing capabilities. So it reduces the need to introduce new devices all the time. You can sort of, if you can model them as a collection of existing capabilities, then you can proceed. All right, next slide. Now, the Web of Things is a project which has currently been chartered. There's a working group. We're aiming for a candidate recommendation by the end of 2018. There's currently a draft spec out if you want to take a look at it. But the Web of Things working group actually has 3 deliverables. The most important one for this discussion is the thing description. So the basic idea of the Web of Things is rather than having a prescriptive standard that says to get interoperability, your device must do things this way. If everyone does things this way, then they interoperate, which is the approach of most standards. The Web of Things approach says, okay, give me your device, and I will describe it with metadata, and then other devices can consume that metadata and then can interoperate with it. So the advantage of the descriptive approach is you can do it after the fact. The device can be shipped, it can be out there, it can be working, and then you can go and write the thing description for it and then interoperate with it. This is very, very important in the handle brownfield problem in IoT. There's already devices out there. No one's going to tear them out to replace them with new devices just to get interoperability. So the sort of, test in advance and then ensure it works before it's installed is fine for new devices, for greenfield, but it doesn't really handle the brownfield problem. So the descriptive approach handles the brownfield problem without requiring additional gateways, basically. You can always add gateways, you can always do the translation, but if you can have a powerful enough description, you don't necessarily have to. Okay, next slide. So this is a simple example of a thing description, and basically it's a JSON LD file. And JSON, you're probably all familiar with. JSON LD is a serialization of a resource description, which is a semantic web triple store. And so it takes semantic information and it's been serialized. But it can also be interpreted as a simple JSON file. So the stuff in highlighted colors here actually relates to the semantic capabilities of this file. So the green parts on top point at vocabularies that are being used, And you can actually define prefixes or namespaces like IoT and HTTP here. And then within the file, you can use terms from those vocabularies with the appropriate prefix. So in the case of IoT prefix, we're actually using terms from the IoTschema.org vocabulary. And so, for example, we can indicate that there's a certain property in this device, which is the IoT switch status, which actually represents the on-off state of this light. Okay, and now we can see that standard term. We have a relationship to a vocabulary that's been standardized, and we can programmatically scan for that standard term. And next slide. The thing description also includes similar concepts to JSON schema, so it also describes the structure of the payload. Now, payloads may not be necessarily JSON, but we can still describe the structure of them with a JSON equivalence, with the assumption that we can convert to and from JSON. Okay, let's go to the next slide. This gives you an example. So the last thing I wanted to do was talk about some proofs of concepts that we built at the Web of Things Plugfest. And the goals of proof of concepts are to understand what the heck we're doing. And so we kind of want to, mash together various technologies and see how they work together and find the gaps, and then iterate and try and fill in the gaps for time. These are also very useful to demonstrate to business people, what's the value of a certain set of technologies or standards. So I'm just going to walk you through a POC plan that I've been working on within the W3C work. Next slide. So actually, I'm about halfway through this plan, and these are the 4 steps I'm aiming for. Eventually, I'm going to look at kind of an ambient computing type programming model. But right now, I'm still on steps 1 and 2, working through metadata bridging and semantic use case. So I'm only going to talk about the first 2 steps, but my next step after this is doing fog integration. Okay, first step is metadata bridging. Next slide. So basically, there's lots of different standards out there, and they all have their own metadata. So what I wanted to do was automatically, without human intervention, basically, digest metadata from some existing standard and translate it into Web of Things. And the idea is that rather than bridging the data, which is a runtime issue, let's bridge the metadata, which is much more static. And so basically, I targeted OCF metadata. I use introspection. I grab the metadata out of OCF and I translate it into Web of Things. Along the way, I also applied IoTschema.org vocabulary by basically assigning those kinds of vocabulary to OCF concepts, namely resource types. And so basically, OCF devices are collections of certain resource types, and so I can associate IoTschema.org capabilities with those resource types, and then generate a thing description. I then programmatically, again, automatically, registered those thing descriptions with a thing directory, which I'll discuss in a minute. Which actually gives me a semantic search capability, because a thing directory actually is what's called a Sparkle endpoint, lets me do semantic queries on the set of all things registered with it. I also had to do various other annoying things like NAT traversal and security, etc., but I won't talk about that here. Next slide. So this is like, all the bits and pieces for the little thing, and so you can see there's also a NAT traversal issue going on. But the metadata bridge basically was using introspection across OCF devices. Now, in addition to the OCF metadata, there's also auxiliary metadata. So basically, there may not be information in the OCF metadata, but you maybe can associate information with particular OCF metadata like resource types or even manufacturer IDs. And then you can attach that to the thing descriptions as you generate them. So one of the ideas here is that we can harvest information from multiple sources and integrate it together into a single semantic model for IoT devices. And then we register that with a searchable thing directory that supports semantic queries. Next slide. And this is kind of the test setup. And actually, there's a whole room full of devices here. I'm just showing you one desk. But basically, we have a bunch of devices from different vendors, and there's a gateway in here too, and edge devices. and they're all registering themselves with this this gateway. Next slide. So anyways, this actually is thing description was automatically generated from OCF metadata and registered with a thing description. Actually, let's just skip this because we already saw it. Next slide. Next slide. Okay, so the thing directory's other piece that's interesting. This is actually an open source project associated with Web of Things, but basically you can take a thing description and you can, it's a web service interface, you can register the thing description with the thing directory. And then you can do another service entry point in the web API of the thing directory, lets you do semantic searches. And you can basically do Sparkle queries, which let you do searches for semantic terms. Now, the important thing about the semantic terms is they can be associated with each other. You don't have to search for the exact same term. You can search for a term that's related through some semantic relationship with the term in the thing directory, which gives you a lot of flexibility in the system. You can also register different kinds of terms like locations or energy consumption or whatever you want with the thing description. The other thing that's interesting about Sparkle is that you can federate them. So multiple Sparkle endpoints can actually pull data from each other. So a thing directory isn't just a standalone thing. It can be part of a network of federated databases that then pull things together. So you actually get a distributed system for doing search. One problem I want to point out has not been dealt with is security. Is how do I limit my semantic searches to just the devices that I am allowed to search? That is still an open problem. It has been dealt with in semantic search generally, but not in the context of IoT yet. Next slide. We also discovered various limitations in IoTschema.org. It's actually a pretty limited ontology right now. It's got a lot of inconsistencies in terminology. Some of these are just bike shed issues, but some are, there's no like humidity sensor, there's no like this, and there's no that. So there's a lot of issues. These are just, I think, maturity problems. I think the basic structure is pretty good, and it's just a matter of filling in a lot of blanks and cleaning up some of these issues. One of the nice things, though, about the whole structure is you don't have to use IoTschema.org. It just was selected. We can use other ontologies. In fact, we can have multiple thing descriptions with different ontologies and just relate them to each other with a third ontology. So that's a little messy, but it is possible, and so it's feasible to do bridging between different semantics. So I think the strategy here is just plow ahead, use whatever ontology we can get our hands on, and iterate over time until we can converge on something. I think the sooner we can have a common solid ontology that everyone uses, the better off we'll be. But it isn't really a blocking issue that stops us today from going ahead and starting to do things like this. Okay, and I'm sorry I'm going so fast, but I know we're running late today. One thing I didn't quite get done, but I wanted to do was semantic voice control. So the idea here is that things like Amazon Voice Services have their own set of semantics, their own set of intents associated with voice control. And I wanted to correlate that with the semantics of IoTschema.org. And so, so now that I have a web service, the thing directory, that allows me to do semantic queries and to find things and to talk to things with their interfaces, I also can access that from an AVS service that can use those searches to find entry points, do certain things like turn lights on and off or whatever. And so the next step here is to write an Alexa adapter that actually does semantic queries to find useful things to do given a certain voice intent. Now, I actually did a little look at, I did correlate all the semantic information from AVS. Next slide. Actually, let's just skip this as the architecture. Next slide. Yeah, so actually let's go back one. So AVS itself, of course, is a cloud service, but it also makes an assumption there's a device cloud that has to have a global URL. So you need an entry point into the system which is globally visible, so basically outside your NAP. And so you have to deal with all the issues of NAT traversal. Then you have to write this adapter to be able to take intents from AVS and translate them into commands to your device cloud. I should mention there's two ways to do AVS IoT control. There's a home skill, which is a set of predefined intents, or you can do a custom skill, which you can do whatever you want, and you can do your own intents. So I just went through on the next few slides. I collected the semantics of the predefined home skill, and it actually matches up pretty well with a lot of the intents already defined for IoTschema.org. Next slide. And in particular, there is this concept of capabilities in the home skill, and these don't quite match one-to-one with the capabilities in IoTschema.org, but they're pretty close. Now, there is also a couple other things that AVS does. So there's the idea of bundling, so getting state while doing an action. There's both absolute and relative mechanisms to adjust properties, which isn't really something that is generally available. These are all things that can be dealt with by having digital twins or device shadows. So for example, to do relative adjustments, you can have a device shadow that gets the current value, updates it, and writes it back. These kind of adapters can be part of the whole entire system. Next. Oh, actually, one more thing to mention is that devices can also self-report the capabilities. So there is an introspection mechanism also available that you want to report capabilities back to Amazon about what a device can do. Another place where the thing description is useful because you can read the thing description and then report back to the AVS system what a device can do. Anyways, AVS has a set of capabilities. Here's some examples, power controller, turning things on and off. Obviously, that maps to what I showed you with the power on-off state, temperatures and brightness and so forth. So actually, AVS home skills are still pretty limited to the set of devices that are typically shipping right now. And also, as you'll note, it's very home-oriented, which is probably typical of like voice control. I think one thing we need to do is look beyond home, obviously, but it's a reasonable place to start, but we shouldn't stop there. Anyways, just to give you an idea, you can look at this later on, but there's a lot of predefined capabilities, and these do map relatively nicely, but not exactly one-to-one onto IoTschema.org. Next slide. Yeah, there's also things with thermostats. One additional thing that's worth noting is that AVS is very picky about the time it takes to take something to respond. So if you respond in less than 8 seconds, it will assume that it failed and will cancel it. So if you have a longer running state, you have to deal with it in a multiple step process. And that requires, there's also an eventing mechanism that you have to deal with for updating state asynchronously. So a lot of these things aren't necessarily supported by the device, in which case you would also need a device shadow to deal with those things. Next step. Next slide.
Okay, Michael, we have about 2 minutes session time left, so I hope you can start to wrap up.
And finally, there's just a bunch of management stuff that it raises a bunch of interesting questions. Is what are some generic management capabilities you want to have in devices, and even for things like fog systems. So, for example, there's a message to check: is the IoT device connected? Can you reach it in the cloud? And this is actually a pretty general statement to make about any IoT device. Next slide. Okay, so just to wrap up, interoperability is very important. There's some interesting stuff we can do with semantic search, which is already a well-defined technology supported by W3C standards. So how can we leverage that? We built a little test system that was actually pretty cool that let us do semantic search across IoT devices. And this leverages a standard we're working on with W3C for describing the metadata of things. And this descriptor approach to standards is actually very useful for brownfield systems. We have a lot of work to do, and I think the way to deal with that and to understand what's needed in the gaps is to work through some concrete scenarios. Right now, we've only done very simple home-based scenarios. We need to do industrial scenarios as well. Finally, in the long run, we need to include fog computing. I don't consider IoT to be just edge devices or small constrained devices. I consider it to be everything that provides services that include these small edge devices. That means it includes fog, it includes the cloud, it includes the network. And so we need to think about all these pieces fit together into an overall system. All right, I will stop there. And
so thank you, Michael. I think that that was pretty impressive and lays out a number of paths we can go forward. So by now the session time is over, so I don't think we have time for questions. The buses here are leaving in 10 minutes for this trip. So thank you for the presentation and enjoy the day over there in the USA.
Okay, bye everyone. Thanks a lot.
Okay, thank you, Michael, and thank you everyone for joining the session today. For more information about the future meetings, please follow the T2TRG list, and especially the Wishy activity we have on the wishy.space in the GitHub wiki. We have more information about the future calls, so please do attend those on the topics that you are interested of. And if you haven't signed yet the blue sheets, please do before you leave. Thank you.
I know you.